So this is 4 beta. We're just going to set this problem up. So think about what you did yesterday with the rectangle that was beneath the sine wave, and tell me, what's the x coordinate? What's this coordinate right here? On the bottom of this rectangle, what do you think you call that? It's your unknown. It's x. So if that's x, what is the base of this rectangle? 2x, yes. So the rectangle is 2x is the width. How tall is the rectangle? Yeah, here's the height. The height is the y-axis. So which of these curves is the higher curve? One is opening down, which would be 30 plus a negative x squared. So this value right here, think about this. So I'm pointing northeast intersection. The coordinates of that point would be x units to the right, up 30 plus a negative x squared. That would be the height. This southeast corner will be x units to the right, up 4x squared. And the height of the rectangle would be this, take away this. So it would be 30 plus a negative x squared, subtract 4x squared. That value, subtract that value. Now think about this. Here's that one. Here's 30 plus a negative x squared. If I subtract the 4x squared, you're taking away this blue height. What are you left with? The height of the rectangle. Is it logical? So now what? So now you have this, which would be the area. The area of this thing, constant and expected x, would be 2x times 30 plus a negative 5x squared. Now the problem's done. Why? Because you distribute this, okay? We can go to lattice, we don't have to go. You have 60x subtract 10x cubed. That's a of x. If you differentiate this and set it equal to 0, what are you looking for? What value of x makes the derivative 0, where a value prior to that is positive, the derivative is positive, the variable is growing. And then there's a sign change where it goes negative. Does that make sense? This has to be your approach to the questions. Like you don't just start on take a couple minutes, think down. Right? That's the approach. You go on H chart. If I walk around the room, you don't have an H chart, you're not with us all the time. So here's the work. Here's the 60x, it's a negative 10x cubed. The derivatives here, the greatest common factor is a 30. So x squared is root 2. So x is root 2. So all x is root 2. This is about 1.7, yes? So I put two numbers in here, for 1 and a 2. And I go to the derivative. If I put a 1 in here in the derivative, 30, 60 subtract 30. 30 is positive. If I put a 2 in here, 2 squared is 4. 30 times 4 is 120. 60 subtract 120 is at negative 60. It's negative. So between 1 and 2, the derivative goes from positive to negative. So in between, you have a maximum value. So the parent curve is going up until you got the root 2, and then it goes down. So now what? Well, what was the choices? The multiple choice. Root 2 is not a choice. They want the area of the rectangle. You're going to put root 2, see instead of this, the area, and you would get E, which is 40 root 2. Right? So, example 5. So you're going to go in the book, here's the econ question. And we're looking at page 224. Suppose that R of X, now ready? R is revenue. If you happen to have a business flash, I'm talking about revenue. It's the amount of money you bring in. So if you have a job and you work at Juice Box, who works there? No one? 21? Work line? And you get the opening check, so they give you money to put the tax on, so they change. There's probably $100 in there in small bill. At the end of your shift, there's $350 in it. So the revenue is $250. Revenue. You're paying the expense of that, just is revenue. Then in this problem, the cost function. So they give you a revenue function, which is linear, and a cost function, which is the cubic. And there's a picture in the book on page 224 in the margin. So here's the picture. Okay? So the red curve is a revenue curve. So you work at Juice Box. How can you make this fund work? If every time you buy a juice box, it costs $9. There's a lot of juice boxes? Right. But if the revenue is 9x, that means 9 times however many products you sold. To make this user friendly, we're going to say we only sell one product. We sell juice boxes and they're $9 each. Now, ready? You're an FBLA. You can have an idea. You can recommend as a fundraiser, and in the spring, to raise money for FBLA, you can sell juice boxes for $9 each. Okay, that's one idea. You can use. So that's the red curve. The blue curve is a cubic. That's how much it costs. What's happening? In the beginning, your cost is up because you have to buy materials, you have to pay electricity. Make sense? You've got stuff up front costs. You have to pay your rent. And then as you sell some, that gets distributed over many more products, and you get to a point where it doesn't help anymore. But look what you're looking for. You're looking for the derivative of the curve, the derivative of the cost curve, the tangent. The tangent, which happens at the derivative of the cost curve, being parallel to the revenue curve, because that's where they would be furthest apart. What's happening? Well, here when they're parallel, the blue curve is above the red curve. So costs are higher than revenue. Not good. Here, the red curve is above the blue curve. The revenue is higher than cost. That's good. Meaning what? Meaning this is the number of juice boxes to have ready. Because after that, you're getting more money in the register, but you're not getting more profits. You're going to be able to play chess here, not checkers. I just want to sell as many products as possible. There you go. You want to maximize your revenue. So, how do we do this? We say, here's revenue, here's cost. Here's the derivative of revenue, the derivative of cost. Subtract them. Subtract them and set it equal to 0. Okay? When is the derivative equal to 0? Which is in effect the difference in the derivatives, once that equals 0. Here and here. Then I check points on either side of that to confirm whether you have a min or max. In this case, we're looking for the maximum difference between revenue and cost. And then we have this picture. Ready? Here is revenue take away cost in Y1. That is this curve. That PDF is pre-colon calculated. Then I turn on the numerical derivative. But this should make sense to you. This is like the, that picture should make sense to you. This is like what we did with the big derivative plot. The thicker graph is the derivative. So what do you have here? The derivative 0. But it's going from negative to positive. So the parent graph is going from falling to rising. It's a mean. Here's the mean directly below that. And look here. There's another 0 for the derivative. The derivative is going from positive to negative. So the parent graph is going from rising to falling. That's what I want. That value should be the maximum profit. So all they're doing is taking what you did earlier and trying to make it interesting in context of something you would do outside of school. So leave that up there. That's your model. You're going to go to problem 23. So the revenue is 8 times x to 1/2. The cost is that. So you differentiate them both with the power rule. The difference between R prime of x and C prime of x is here. Set the derivative, the difference of the derivative is equal to 0. Here's your algebra. Add 4x to both sides. Divide both sides by 4. And you would have x equals x to negative 1/2. They multiply root x on both sides. You get a 1 on the right. X times x to 1/2 is x to 3/2. Make it 2/3 power of each side, you get a 1. The question is in terms of 1,000. So it's 1,000 units. We what? If I put a number below 1 in the derivative, I get a positive answer. If I put a number above, it's 3.6. If I put a number above 1, put a 2, I get a negative value. So what's that telling you? It's telling you the parent graph is increasing, then began to decrease, and the value of the function at 1,000 is 6, which tells you how much money you need. Okay? Which was revenue takeaway costs. So, that is it for the beta lesson.